In this video, we are going to see about formation of PN junction diode. Junction diode is formed by placing a P-type crystal in contact with N-type crystal and subjecting to high pressure so that it becomes a single piece. The assembly so obtained is called PN junction or junction diode or crystal diode. The surface of contact of P and N-type crystal is called junction. The P-type region has holes as majority charge carriers. Similarly, the N-type region has electron as majority charge carriers. In this diagram, we clearly see the P-type region has holes as majority carriers and electrons as minority carriers. And N-type region has electron as majority carriers and holes as minority carriers. Both are connected to the battery and we can see the junction, which is the surface of contact of P and N-type crystal. The region which become depleted of the mobile charge carrier is called depletion region. In addition to these majority charge carriers, there are few minority charge carriers in each region. The P region contains a few electrons while the N region contains a few holes. Thus, we find that at the junction there is a decreasing hole concentration from left to right, which makes the hole diffuses from P side to N side. Similarly, electron diffuse from right to left across the junction. Holes leaving and electrons entering the P side make it negative. Similarly, holes entering and electron leaving the N side make it positive. Thus, there is a net negative charge on the P side of the region and net positive charge on the N side. This produces an electric field across the junction as if the fictitious battery is connected with its positive terminal to N and negative terminal to P section. Equilibrium is established when the field becomes large enough to stop further diffusion of majority charge carriers. The field, however, helps the minority carriers to move across the junction. The region on either side of the junction which become depleted of the mobile charge carriers is called depletion region. The thickness of this region is of the order of 10 power minus 6 meter. The potential difference across the depletion region is called the potential barrier. This is the explanation for formation of PN junction diode. Thank you.
Hello everyone, this is A. Preetita from 3rd BSc Physics, studying in Dr. Umayal Ramanathan College for Women, Karaikudi. My unit is Analog Electronics and my topic is relationship between alpha and beta. Here I am deriving the relationship between alpha and beta of BJT. As we know, the emitter current is equal to collector current plus base current. So the relationship between IC and IE with respect to alpha, if we define alpha equal to IC by IE. Similarly, the relationship between the collector current and the base current, that is beta, equal to IC by IB. By using this expression, we can derive the relationship between the alpha and beta. First, let us take the expression of current IE equal to IC plus IB. IC by alpha equal to IC plus IC by beta gives 1 by alpha equal to 1. Beta equal to alpha beta plus alpha equal to beta plus 1 into alpha. The expression becomes alpha equal to beta by beta plus 1 and beta equal to alpha by alpha minus 1, where IC is the current flowing into the collector terminal, IB is the current flowing into the base terminal, and IE is the current flowing out of the emitter terminal.
In this video, we are going to study about the AC and DC equivalent circuit. Transistor amplifier, both DC and AC conditions prevail. The DC source set up the DC current and voltage, whereas the AC source, that is signal, produce the fluctuations in the transistor current and voltages. Therefore, a simple way to analyze the action of transistor in a split to the analysis into the two parts, that is AC analysis and DC analysis. In the DC analysis, where we consider all DC sources at the same time and work out the DC current and voltage in the circuit. On the other hand, for a AC analysis, we consider all AC sources at the same time and work out the AC current and voltages. The circuit can be easily analyzed by splitting into the DC equivalent circuit and AC equivalent circuit. This is circuit of AC and DC equivalent circuit. This is base, this is collector, and this is emitter. This is R1 and R2. This is RC. This is RE and this is RL. Next, we are going to DC equivalent circuit. In the DC equivalent circuit of transistor amplifier, it is only considered in DC conditions. That is, it presumes that no signal is applied. The direct current cannot flow through the capacitor. The capacitor is always open circuit in the DC equivalent circuit. Therefore, the order through the equivalent circuit, the following the two steps. The first one is reduce all AC source to 0. Second one is open all capacitors. It is easily calculated the DC current and voltage from the circuit. This is circuit of DC equivalent circuit. This is R1 and R2. This is RC and RE. This is plus VCC. Next, the AC equivalent circuit. In the AC equivalent circuit of transistor amplifier, it is only considered the AC conditions. The DC voltage is not important for the circuit, maybe it considered 0. The capacitors are generally used to couple or bypass the AC signal. The capacitors that does appears in the short circuit of AC signals. The AC equivalent circuit, the following the two steps. First, reduce all DC source to 0. Second, short all the capacitors. It is easily calculated the AC current and voltages for this circuit. This is the circuit of AC equivalent circuit. This is base, this is collector, and this is emitter. This is R1 and R2. This is RC and RL. It may be seen that the total current in any branch is the sum of DC and AC current through the branch. Similarly, the total voltage across any branch is sum of the AC and DC of voltages across the branch. Thank you.
Now we are going to see transistor audio power amplifier. A transistor amplifier which raises the power level of the signals that have audio frequency range is known as transistor audio power amplifier. In general, the last stage of the multi-stage amplifier is the power stage. The power amplifier differs from all the previous stages in that here a concentrated effort is made to obtain maximum output power. A transistor that is suitable for power amplification is generally known as power transistor. It differs from other transistors mostly in size. It is considerably larger to provide for handling the great amount of power. Audio power amplifiers are used to deliver a large amount of power to a low resistance load. Typically, load values range from 300 ohm to 8 ohm. Although these load values do not cover every possibility, they do illustrate the fact that audio power amplifiers usually drive low resistance loads. The typical power output rating of a power amplifier is 1 watt or more. So here is a transistor audio power amplifier. Next is the difference between voltage and power amplifiers. The distance between voltage and power amplifiers is somewhat artificial since useful power, that is product of voltage and current, is always developed in the load resistance through which current flows. The difference between the two types is really one of degree. It is a question of how much voltage and how much power. A voltage amplifier is designed to achieve maximum voltage amplification. It is, however, not important to raise the power level. On the other hand, a power amplifier is designed to obtain maximum output power. So the first one is the voltage amplifier. The voltage gain of an amplifier is given by AV is equal to beta into RC by Rin. In order to achieve high voltage amplification, the following features are incorporated in such amplifiers. First point is that the transistor with high beta is used in the circuit. In other words, those transistors are employed which have thin base. Second point, the input resistance Rn of the transistor is sought to be quite low as compared to the collector load Rc. Third point, a relatively high load Rc is used in the collector. To permit this condition, voltage amplifiers are always operated at low collector currents. If the collector current is small, we can use large RC in the collector circuit. The second one is the power amplifier. A power amplifier is required to deliver a large amount of power, and as such, it has to handle large current. In order to achieve high power amplification, the following features are incorporated in such amplifiers. First point, the size of the power transistor is made considerably larger in order to dissipate the heat produced in the transistor during operation. Second point, the base is made thicker to handle large currents. In other words, transistors with comparatively smaller beta are used. Third point, transformer coupling is used for impedance matching. Next is the comparison between voltage and power amplifiers. So particular voltage amplifier, power amplifier. In beta, high in voltage amplifier, low in power amplifier. RC, high in voltage amplifier, low in power amplifier. Coupling, usually RC coupling in voltage amplifier, invariably transformer coupling in power amplifier. Input voltage, low in voltage amplifier, high in power amplifier. Collector current, low in voltage amplifier, high in power amplifier. Power output, low in voltage amplifier, high in power amplifier. Output impedance, high in voltage amplifier, low in power amplifier. Thank you.
I am K. Gayatri from 3rd BSc Physics, Dr. Umayal Ramanathan College for Women, Karaikudi. My subject name is Analog Electronics, Unit 5, topic Non-Inverting Amplifier. In this video, we are going to learn about the non-inverting amplifier. Non-inverting operational amplifier is when the signal is applied at the non-inverting input. The resulting circuit is known as non-inverting op-amp. In this amplifier, the output is exactly in phase without the input. That is, when the positive voltage is applied to the circuit, the output will be also positive. Be assuming the operational amplifier is ideal, then concept of visual short can be applied. That is, the voltage at the inverting and non-inverting terminal is equal. Since it is a non-inverting amplifier, the input signal is applied to the non-inverting input. The output is applied back to the input through the feedback circuit formed by feedback resistor RF and input resistance RI. And next, note the resistors RF and RI from the voltage divided at the inverting input. This produces negative feedback in this circuit. Note that Ri is grounded since the input signal is applied to the non-inverting input, and next the output signal will be non-inverted, that is the output signal will be in phase with the input signal, hence the name is non-inverting amplifier. The potential at the point A is same in Vn since the input impedance of the op-amp is very high. all the current it flow through RF also flow through RI. And next, voltage across RI equal to 0 minus V in. And next, voltage across RF equal to V out minus V in. Now current through RI is equal to current through RF. Vn minus 0 by Ri equal to Vout minus Vin by RF. V in RF equal to V out Ri minus V in Ri. And next, V in is RF plus Ri is equal to V out Ri. And then V out divided by V in equal to RF plus Ri by Ri. And next, then the closed loop voltage gain, the non-inverting operational amplifier will be gained as AV equal to V out divided by V in equal to 1 plus RF by Ri. Thus, the voltage gain of the non-inverting amplifier also depend upon the values of RF and Ri. The voltage gain of the non-inverting amplifier can be made equal to or greater than 1. The voltage gain of the non-inverting amplifier will always be greater than the gain of the equivalent inverting amplifier by the value of 1. Next, the voltage gain is positive since the output signal is phase with the input signal. Thank you.